Hello everyone, we will now begin the Alpha project presentation by Team SafeMotion. Our team members are as follows. I am the team leader, Kangjun Lee. Tesla and Waymo are testing Mapless or map-like autonomy in complex cities, suggesting HT maps are not strictly required. However, most commercial systems still rely on HT maps, which are costly and quickly outdated. Our platform uses 6 synchronized surrounded cameras and 32-channel Hesai LiDAR and GPS IMU for pose, 2 Nuvo PCs, split-core navigation control, and real-time LiDAR processing. In the camera pipeline, we implement a bird's-eye view transformation. We tune a 3x3 homography to convert the front view into a top-down world view. After many trials, we found parameters that keep both lanes visible on curves, giving a stable bird's-eye view across different road shapes. To achieve real-time performance, we accelerate processing with NVIDIA CUDA. This makes lane processing about 10 times faster than CPU only. Lower latency lets the vehicle react quickly, which is critical for safe steering and dynamic scenes. Next, we use YOLO as our core vision model. It outputs lane geometry and drivable area segmentation at the same time, which both results we identify road boundaries and safe driving space, providing a reliable foundation for navigation. Then we feed lane curves using Rensec and lasso regression. To reduce jitter, we apply EMA smoothing with confidence decay. If one lane disappears briefly, we estimate it using a standard lane width and keep the center line stable. As ongoing work, we are building HSV-based lane color detection. It separates yellow center lines from white lane lines under changing lighting. This will help prevent illegal crossings and support safer lane change decisions. In mapless driving, we can predefine a tight LiDAR ROI, so the point cloud includes a lot of roadside clutter, which increases computation and can create inappropriate objects. To handle this, we keep a wide ROI but apply a lightweight object filtering to remove invalid detections early. Our filtering is rule-based. We reject objects using simple bounding box constraints: width, length, and height. This works well for common roadside clutter. For example, if an object has a very small footprint but is unusually tall, we treat it as a tree rather than a vehicle. Filtering is ineffective for unreliable clusters, like when multiple vegetation points merge into one, appearing as a vehicle. This occurs due to high clustering tolerance. Since LiDAR's z-axis points are sparse, we need to find a way to reduce the tolerance. To make clustering stable, we downsample the point cloud only along the z-axis and run clustering on the simplified data, then restore the original point density. We also use distance-dependent tolerance. Near objects use a small tolerance and far objects use a larger one. With this process, we can obtain these clean and accurate clusters. In laneless areas like intersections or open plazas, lane markings can disappear. In these segments, we rely on LiDAR and GPS-based motion estimation to maintain the route until the lane cues return. For mapless segments like intersections, we use KISS ICP, a lightweight LiDAR-based odometry that ensures stable routing when lane cues are lost. It offers efficient processing, making it ideal for real-time driving alongside heavy module like deep learning. PID control adjusts 3 terms: P for current error, I for steady-state error, and D for damping oscillations. Tuning these gains balances fast response and stability. This video shows our PID-based cruise control. We set the target speed like 23 km and compute the speed error. PID output is mapped to throttle or brake. ACC follows a preset speed when no leader is detected. With a leader, a PID controller adjusts acceleration based on distance error and speed, smoothly maintaining a safe gap. This slide explains our normal vector lane centering. We pick a reference point on the center lane and estimate its tangent direction. Along the normal line, we find the nearest left and right boundaries and take the midpoint at the target. This slide shows the effect of noise. Projecting jittered lane points onto the normal direction keeps the target near the center. The curvature-based bias neutralizes inward jumps, stabilizing steering and improving lane centering. The current obstacle module detects objects on the path and estimates their speed, stopping the vehicle if risk increases. Future work includes improving LiDAR camera calibration and enhancing lane tracking to enable automatic lane changes instead of stopping.